Hi everyone, my name is Sivakumar and this is a Group 3's project for microprocessors and digital systems. I'm joined here with Aidan Barber, Aidan Vine, Julius Atherton, and Harnoordeep Grewal. Next slide, please. So the objective of this microprocessors and digital systems project report is to display our understanding of the knowledge gained throughout the semester from the lectures as well as the labs. And the team was going to accomplish this by designing a digital circuit, which will incorporate a 7-segment display with the Xillinx software. Next slide, please.
For our design, the goal of this 7-segment display is to simulate a word guessing game. For this game, the user guesses a 5-letter word and the system checks how many of the letters they have guessed correctly along with their positioning. The letters for the word shall be represented using the 7-segment display. In the case of our design, the correct word shall be cyber, and the team will test this by initially putting several wrong answers before finally putting the correct answers to see how the program responds. There were two main truth tables required for this design. The first representing the latch sequences which were used for comparison between the guessed and stored word. Table 2 here represents the combinations of 7-bit numbers needed to display the corresponding symbols of the words. Next.
Here's our logic circuit, which we constructed before coding the circuit in Xillinx. As you can see, our circuit is constructed of two 35-bit registers, two 7-bit registers, and a 5-bit register. There's also a latch, a clock, and a 5-digit 7-segment display, and lastly, an XOR gate and 7 AND gates. The guessed word is compared to the stored word, where the latch is used to then complete the letter if it is the same. If a letter is the same, it is displayed to the 7-segment displayed, and if not, the segment on the display is left blank.
Now we will be explaining the code. The first segment of the code, which can be seen here, is mainly for initializing variables and gathering libraries. The code starts with gathering several libraries at the top. Afterwards, an entity is created consisting of the values we will use to represent the 7-segment display. They are initially set to 0 as the user has not entered a word yet. After this, the signal SW command sets the value of the stored word, and the user will place their guess in the signal GW portion. The final portion of the code declares the remaining required variables under the signal type. These are primarily for latches and counters. Next.
So in this section, essentially what we're having is starting with creating temporary placeholders for the last segment in each counter. This is so that when they rotate through, we actually have the last variable to put back into the counter. When we have a rising edge occur, the code will check if the 7-segment counter register has completed a full letter, shifting the 5-bit counter to eventually move to the next letter in the display. After that, we will have the latch be set to 0 when XNOR reads that the guessed word bit and the stored word bit are different. And this will then shift the bits of the 7-segment letter register and the 7 counter register. Next.
All right, for part 3, we'll be setting up this part of the code. The first thing that we do is we instantiate a for loop where we go and we iterate through the 35 bits of the saved word that we have set up. And the saved word is the word that we have saved, which is cyber. And we are going to iterate through all 7 letters of this by going through each of the 35 bits. We also set up a temporary SW, and this is so that we implement the last bit because it gets pushed out and we want to bring it back in again. We do almost the exact same thing for the guessed word as well, where we iterate through all 35 bits of this word. And the guessed word is the word that the user inputs. Therefore, we have tried inputting SOAR in a later test. And we're gonna iterate through all 35 bits of SOAR. And then we're going to bring back the last bit in by using the temporary GW. Because we're not able to compare on the rising edge, we are going to compare on the falling edge. And this is so that we can be able to see how the bits match for the GW versus the SW. And if the latch is true, the letter will be pushed forward.
So as you can see for the last part of code right here, is used to check if the latch is 0, or in other words, false. Then nothing will be displayed, and it's just because false character is the true character needs to be. Next slide, please.
Here you can see the simulation where you can see our stored word, which we're comparing against is cyber, and the guess word in this case is John's. If you see the output when that happens is all zeros to the display, that's because none of the letters match the letters in cyber. Next slide. Here we guessed cheer, which has some letters which it shares with cyber. As you can see, the C, the E, and the R are all displayed in the correct position on the display. And the letter not shared, the H and the E, are left out on the display as they're not shared with cyber. And as you can see on our last simulation here, all the letters are the same as we've guessed cyber, and because of this, cyber is completely displayed to the screen.
Upon the completion of this project, our group has demonstrated our understanding of the core's concept and the materials by successfully designing a model and simulating a digital circuit within a 7-segment display in Xillinx software. The word guessing game simulation circuit correctly outputs our desired result for the word cyber. Several incorrect inputs were tested, with each one being closer to the keyword than the last. Each time the display correctly featured the correct letters along with their position until the correct word had been inputted. In addition to fulfilling the purpose of the course project, the group had also gained the required knowledge to complete further projects involving digital circuits and 7-segment displays. Thus, we are now able to simulate in Xillinx. This understanding has provided us with practical knowledge expressing the difficulties and methods for analysis when applying our theoretical studies to real-world applications. In the future, we can now take this program and go one step further as we would look to make an input that would be more desirable to the customer. Thank you for our project and for teaching this course. Have a nice day.